Okay, I think the first thing I probably had introduced was the IV characteristics of an ideal source. I think everyone by now probably is pretty clear about it, but I'll go ahead and just introduce that real quickly. So when I give you a ideal voltage source, what it means is that doesn't matter what the current is flowing through it, that is basically this I, the voltage across this is always V naught. So if I draw this IV characteristics, no matter what current is flowing through it, negative or positive current, this will be always V naught. Now, in reality, like I had mentioned earlier, that you'll probably have some series resistance called RS, and that will change this characteristics curve by putting a slope on this, depending on how much RS you have, right? So that's the ideal voltage source. So whenever you have an ideal voltage source in a circuit, if there is no source impedance, for example, or even if there is a source impedance, the voltage across this is always V naught. Just remember that, okay? So same thing with I naught, ideal current source. If I give you ideal current source, then doesn't matter what the voltage across it is, the current through it is always I naught. Okay. And now, just like the voltage source, usually, and this is a Norton equivalent, so you'll have an output impedance which is in parallel to it. So let's say that's also RS. So if you have some finite impedance, then this slope will change, right? Depending on how big or how small impedance you have. But if it is ideal, then it will be just constant. So whenever you're solving circuits, and if you're given an ideal current source, then the current flowing through it is always forced to I naught. Just remember that. So in this question, I think, as I had said earlier, one of the main confusions people have is when you ask them what is a voltage of a certain node, you really need to know the voltage across what. So for example, in this question, I have asked V naught with respect to this node here. Let's call this node A, and V naught with respect to B here. So in order to find that out, if you see, this is a pretty simple loop. So you have 9 volt flowing through 3 kilo ohms resistor. So, let's say this is some I naught flowing here, and then I naught is 9 volt over this total resistance 1K plus 3K. So that's 3 milliamp. So you can find out the voltage across these resistors over here. So 3 milliamps times 1K would be 3 volts here, and then 3 milliamps times 2K would be 6 volt here. So when I ask what is V naught with respect to node A, you can see that node A to node B is plus 3 volt, which means that V naught minus VA will be equal to minus 3 volt, right? So that means V naught with respect to VA equals to minus 3 volt. The second question was what's V naught with respect to B, and that's clearly 6 volt here because V naught minus VB is clearly shown here to be plus 6 volts. So always remember potential. If you are asked about a potential, then you need to know with respect to what, right? With respect to what. But current, obviously, it's a cross section. So any cross section, you find out delta Q over delta T, there's your current. So there is no reference for a current. So if I'm telling you the current through this branch is 3 milliamp, it is 3 milliamp. It's not with respect to anything, correct? So that's one thing keep in mind. Now this problem was just purely using KVL to find out the voltage across this current source. And you can use the principle I've already told you. Like for example, I told you this is ideal voltage source. So the voltage across this is always 5 volt, doesn't matter what. And this is ideal current source, which means that this current is always 1 milliamp. And if I don't have any load here, this node also has to be 1 milliamp, right? Because the KCL here has to agree. Same thing here, then the current flowing through this has to be 1 milliamp in this direction. So you'll have a voltage across this, and that voltage will be 1 milliamp times 1K, that's 1 volt here. and this voltage will be flowing in this direction, because again the KCL has to satisfy in this node, which means that 1 milliamp has to flow in this direction. KCL has to satisfy in this node, 1 milliamp has to flow in that direction. Then once you know all these voltages, the only thing which is missing is here. So you just write the entire KVL equation around the loop. So it's minus, so if you go around the loop in this direction, so minus 5 volts plus 1 volt. So let's say VI is actually already given. This is the direction. So plus VI plus 1 volt. So is equal to 0. So which is VI is 5 minus 2, that's 3 volts, right? So it's a very simple KVL equation. But the trick here is because you're given two ideal sources, you have to be, you have to know, is it the current which is forcing it or the voltage which is forcing the current? And here, since we have ideal current and we have one loop, it's very easy because you know the loop, the current through the loop should be the same. So that's pretty straightforward. So, and then we covered superposition. Just quick introduction on superposition. So just to introduce the idea of it. So if you have a linear system where here I'm calling that linear system H, and if you give a set of input, here it's a subscript of A, and if you get output YA, and if you take that same linear system and give another set of inputs, subscript here B, then you get YB, then the superposition principle basically says if you give both the sets of input together to this linear system, then you can actually add these two outputs which were independently achieved from a set of inputs x1 a, x2a, and so on, and x1 b, x2b, and so on. Okay, so now in electrical engineering example, what it means is that if, let's say for example, you have two inputs, one output, you give one input, the other input is 0, and 0 means say independent sources are 0. So if it's a current source, it will be open. If it's a voltage source, it will be a short. And we'll see an example, which again we had given in the quiz. And you find out the voltage or whatever the current, whatever you're trying to measure, that's Y1. Then you make that input 0 here, and then give a second input, which is V2. You find out Y2. And basically the superposition principle says that if you're giving V1, V2 simultaneously, then you can actually add the linear, the independent outputs Y1, Y2, which will be the same as if you're giving V1, V2 simultaneously, right? So that's really the superposition principle. It's a pretty powerful principle. Use it all the time. So it's very important that you know this. And it's, like I said, it's pretty simple principle. Actually, maybe I'll tell you this question right now. You can think about it. So one of the questions which I was asked in my interview was, it's unrelated to electronics, but it's a pretty nifty question. So the question was this: if I have a plate, iron plate, okay? So you have a square iron plate, and I cut a hole out. So this is the iron plate. I cut a hole out. And the question was, if I heat this, so I put fire here and heat this plate. The question was, this hole here will increase in size or decrease in size? Okay, so basically you take a metal plate, you cut it, and you heat the plate. So the question was, will it increase or decrease? And you're supposed to use the superposition principle, but there is one assumption you have to make, and I'll tell you what that assumption is. You assume that this heating of the plate is actually a linear function. In other words, everything happens linearly. So like, for example, the plate will expand linearly, the hole will expand linearly, whatever it is, but it's a linear. That's the only way you can apply superposition principle, okay? So think about it. All right, so in an electrical example, this is again the same problem I gave during the quiz. So we have this op-amp circuit, and I asked to find out the output for independent voltage sources V2 and V1 using superposition, right? Now, in superposition, like we said, we make one input 0, apply the other input, find out the output response, do the other side, and add them up together. So in this case, if you make V1 equals to 0, basically you ground this, and that's what your resultant circuit will look like. And the reason it looks like is because if you see over here, it's essentially R1, R2 parallel to ground in this node. There is no current flowing through this, so that means the positive node will ground. So that's why you can see the positive node is grounded. And then you apply V2 across this. So this is nothing but a inverting amplifier configuration. And I would definitely encourage, you can obviously derive this, but when you're preparing for interviews, most people will expect you to know these kind of configurations. So I will definitely encourage you to know inverting and a non-inverting outputs directly. So if somebody gives you this R2, R1 in an inverting configuration, you should write that directly. V out over V2 equals to minus R2 over R1. Now, to date, I just derive it myself, and that's okay. But like as I said, in interviews, they expect you to know this. So it's good to just know this configuration. Okay, so that's one set of the output. Since there are two independent outputs, we do the second one similarly. We actually ground this now, V2, and apply the independent source V1. And this one it's a non-inverting configuration, but it's not straightforward because you have to find out what the voltage is here, and that voltage is a non-inverting output over here. So, for example, let's say we call this node Vx, then V out over Vx is a non-inverting configuration, which is 1 plus R2 over R1, right? But then you find out that Vx is actually R2 over R1 plus R2 times V1. You substitute that here, you'll get this expression. And then you add these two, then your V out is R2 over R1 times V1 minus V2. And then I think I had asked in the last part of the question, from this output, tell me what kind of configuration this is. Basically what I wanted from you guys is that tell me that this is a differential amplifier. So it's V1 minus V2 times R2 over R1. So this is a good way of creating a differential amplifier if you just have a singular amplifier, like for example on board and so on. In IC design, we have seen it's much easier to do differential amplifiers. So, but this is a good way if you're doing it on the board. Okay, so that's again another question I had asked was using the superposition principle, find out V1, the voltage across V1, V2. Again, here you apply superposition principle because you can actually solve this by writing the KCL KVL node equations directly. But I always prefer superposition because it's easier to solve it and you get a better feel of the circuit as well. So because there are two independent sources, one is the VBAT, that's one independent source, and then I1, which is also independent source because those are two ideal sources. So when I say independent source, it means it's not controlled by some other voltages. Just VBAT of 10 volt, doesn't matter what current flows through it. I1 equals to 0.2 milliamp, doesn't matter what voltage across is. So you do the same thing. You first make I1 equals to 0, and when you guys should all know by now, if there is an independent current source and if you're making it 0, that means it's open, right? It's Thevenin's, it's a Norton equivalent, so you make it open. So if you make it open, you'll get this circuit here, and you'll find out that V1 minus V2 equals to 5 volts, which is essentially just the resistor divider 10K by 10K, right? Do the second part where you make the VBAT equals to 0. Again, when you make a voltage source 0, you short it because the Thevenin, you short it and you apply back the current source here. Again, it's 0.2 milliamps, and these two resistors are in parallel, which is 5K. So 0.2 times 5K, that should give you minus 1 volt because the current is flowing in this direction here, right? So basically now you add these two voltages, 5 minus 1, that's 4 volts, and that should be your V1 minus V2 because of both the independent sources. Okay, this one is the same circuit, and I asked you to find out Thevenin and Norton equivalent. Again, this is probably you guys are familiar with it, but this is something you don't want to look unfamiliar with, especially in interviews. Thevenin's and Norton you should know right away. So in order to find a Thevenin's equivalent of a circuit, so for example, here it's a two-port network between V1 and V2. So that's your equivalent Thevenin's network. And this voltage is basically what's called the no load voltage across V1, V2. So what it means is that if I don't put any load across these two terminals here, what's the V1, V2? Find that first. And then this RTH is the output impedance. It's the output impedance when all independent sources are 0. Okay. So we'll see how we do that. So for RTH, like as I said, you find all independent sources to 0. So open this, short this, and all it is 10K, two 10Ks in parallel, and that's 5K. So your RTH is 5K. And for VTH, no load voltage, we just derived that to be 4 volts. So that's your Thevenin equivalent. So this is 4 volts, and that's 5K. That's how you find out Thevenin's equivalent of a network, right? Okay, so same network. Now you need to find out, let's say you're asked to find out Norton equivalent. Now the Norton equivalent is this. You have an ideal current source with a parallel output impedance. The way you find out this IN, sometimes called the short circuit current source, is you actually short circuit this and find out what's the current flowing through this, or in this direction if you want to show the current source in that direction. And that'll be your INO, which is the Norton equivalent of the entire circuit. And then for the output impedance, it's the same as your Thevenin's output impedance, where you make all your independent sources 0, find out the output impedance. So it'll be the same as what you found out in the Thevenin's. So here I've shown to find the short circuit current, you basically short circuit V1 to V2. Now again, you have two independent sources. You can directly write the equations, like as I said, the node equations, but it's easier to do it with superposition. So you do the first one where I1 equals to 0, and you find out there is 1 milliamp flowing in this direction here. And then you short VBAT, that's VBAT equals to 0, find out the current, and it shows that the short circuit current in this direction is minus 0.2 milliamps, which means that it's actually flowing in the opposite direction here. So your total Norton equivalent current is 1 milliamp by minus 0.2, that's 0.8 milliamps, right? So you have 0.8 milliamps, and this is the same as before, which is 5K. So that's your Norton equivalent, right? So that's the principle you use pretty much, and we'll give you two-port networks whenever I am at least doing the quiz. I hope that's what they do in the and this was just showing that I wanted to show that both this Norton equivalent and the Thevenin's, they are actually duals. What I mean by dual is, if you are actually taking this and using it in any circuit, you should get exactly the same result. The Norton should not give you a different result than your Thevenin's. And I show that by saying that put a load of 5K. So this was your, this was your Thevenin's before with a 4 volt 5K. So I said, okay, put a load of 5K, find out what the current is. It was 0.4 milliamps. Now let's use the Norton, put that same 5K, and if you, and this was your Norton equivalent you found in the previous problem, 0.8 milliamps at 5K, you find out that it's the same 0.4 milliamps, which it should be. So that's what it means by dual. So you can find, for a network, you can find either a Thevenin's or Norton, but for some circuits, usually a Norton is better than Thevenin's. So for example, if you have a common source amplifier like this, and let's say you have a network here, it's better to find a Thevenin's network because this impedance is infinite, looking into it. So you want to look here as a voltage source. Whereas if I give you a common base amplifier, for example, something like this, where your input is actually here and you have a network here, then you want to find a Norton equivalent for this. because this impedance is low now. If you can do the other also, but you'll get larger errors if you do that. So that's why we use either a Thevenin's or a Norton, depending on the circuit. Okay, so for the frequency response by inspection, now again, obviously I asked you to do this by inspection because at least when I interview people, I want to know how, if they have a feel about, where the poles and zeros are coming. But more importantly, you don't have to know very complex poles and zeros, but very simple analysis. Like when you have a simple RC like this, you should first do it by inspection by saying, okay, what's the circuit at infinite frequency when the capacitor is what? A short, right? Because the impedance is 1 over c omega, so it's a short. What is the frequency response at zero frequency, which is DC? And so that gives you the two asymptotes. And because this is a single pole circuit, you can join those two asymptotes and find the 3 dB point. And I'll show you that how to do that. So that was really the purpose. And I could change this to ARC, and you should use the same principle to find that out. So like I said, for omega equals to 0, the cap is open. So this transfer function should be 0 because none of the Vs makes it through. So the output is 0, right? For infinity, this cap is a short here, which means that Vs is equal, Vout is equal to Vs, which means Vout over Vs equals to 1, right? And I asked to find out, because this will help you draw the Bode plot. So that's why, because usually we try to find out what's the minus 3 dB point, which is in linear terms half of the voltage which is appearing here. So basically I asked here, at what omega V naught is equal to Vs over 2, or rather the magnitude of it, because the phase will be all off. And that will be the case when this, the impedance of the capacitor, which is 1 over j omega c, is equal to R, right? That's when you'll have this V out equals to Vs over 2. So if you write that expression here, you just, and this is the magnitude, you'll see that omega equals to 1 over RC, and that's where you get your pole. So that's really, so in the next plot I show, that's how you draw the Bode plot. So like as I said, you first find out at 0 what it is, you find out at infinity it is equals to 1, and then you find out the half or the minus 3 dB point, and it's asymptote based on that. And usually from this you can actually find out the expression as well if it is a simple expression, because here we know it's 1 0 and 1 pole. So the first thing you can do is write the expression for a 1 0 1 pole system like this, because if it is a 0 at 0, that means you need a S plus 0, which is S. And if there is a pole at 1 over RC, then that's how the denominator will look like, but you don't know what is this gain constant, right? And you can know that by putting at omega equals to infinity, we knew that h omega equals to 1. So you substitute that over here, you'll find that k is equal to RC, and you can write the complete expression as this. But more importantly, get a good feel of the circuit. Like when I give you this, you should be able to, like as I said, do it by inspection over here. Like for example, if I give you the same circuit, but if I give you RC circuit like that, so I can ask you this exact same questions. So what is the response going to look like? So you go through the same mental exercise again, right? At omega equals to 0, this is open, so which means that V out is equal to Vs at omega equals to 0, right? And then do the same thing for omega equals to infinity. This cap is a short, which means the output will be 0. So V out equals to 0 at omega equals to infinity. And so if you want to draw a asymptote of this, so that's your V out over Vs magnitude. So you say, oh, it's 1 at infinity, and I'm sorry, 1 at 0 and 0 at infinity. And you go through the same exercise again. You said, okay, I want to join this, but I want to know the 3 dB point. It's exactly the same exercise again, because you want 1 over omega c magnitude to be equal to R for this node V out to be equal to Vs over 2, which again means it'll happen at omega equals to 1 over RC. So that'll be your halfway point if this was a linear curve, and that's 1 over RC, at which this quantity is half, and this is 1, right? So it's kind of the same principle. So just know that, inductor at omega equals to 0 is a short, capacitor is open, inductor is open at omega equals to infinity, capacitor is a short. So they are like duals of each other. And resistor obviously is the same for all frequencies. Okay. All right, RLC circuits again. I think this is somewhere people get confused quite a bit. And you just follow the basic principles, right? So in this circuit, for example, I made it simple by actually giving you a current source in one loop. If I made this a voltage source, it'll become a little complicated. But if it is a current source, the KCL has to apply everywhere, right? So it has to be I1 all throughout, right? It should be I1 here, I1 in L, I1 in C as well, right? It has, KCL always applies for, this is approximation of a Maxwell's equation where you're assuming the frequency is much lower. So in all these lumped cases, the KCL always applies. So if that applies, then you can find out the voltage across L based on I1, voltage across C based on I1 as well, and then plot this. So I'd ask if I0 is given in this fashion. So from sometimes 0 to sometime T0, I said there's no current flowing through it. All the initial condition obviously is assumed to be 0. And then I give a ramp with some slope of m, and then I stop the ramp and make I0, and I ask to find the voltage at this node V1, which is actually the voltage across the capacitor. And when I say V1, and you can see here I've drawn a ground. So if I've drawn a ground and I ask you to plot a V1, then it is always with respect to that ground, right? So I don't have to tell you with respect to which node. So if you find this ground, then all the voltages are with respect to that. And then same thing, V2 with respect to ground again, which is basically V1 plus whatever inductor voltage is here. So from 0 to T0, like as I said, V1 equals to 0, V2 equals to 0. So that's, these two portions are 0 here. Now from T0 to T1, you have a ramp of a current with some slope M. If you want to find out the voltage across the capacitor, that's the integral of 1 over C times that current. And because it's a slope, it's going to be this quadratic equation. So that's your voltage across V1 here. Now the VL is, it's actually simple. It's a differential of the current flowing through it. Since it's a constant slope, so you'll actually get a jump here like this, right? And that jump is equal to ML. So V2 is this voltage plus whatever you calculated here. So basically it's this voltage plus this jump here. So you get that. And from T1 to, infinity, which is, I haven't put a stop time here. That one for V1 will be equal to whatever voltage was till T0, because it's a capacitor, right? Whatever value is stored, it won't go away immediately. You have to either discharge it or just keep charging it. In this circuit, since I'm pumping the current in the same direction, this capacitor voltage will just keep charging, right? There won't be any discharge. So it was whatever voltage was at V1 T1, and then because it's a constant current source, if you integrate it, you should get this, right? It's an integrator basically. So you'll get an integrating current source. And then VL, because the slope is 0, the voltage across the inductor goes to 0. And V2 is V1 plus VL, which is equal to V1 basically. So you can see this node voltage just keeps increasing. The voltage across V2 drops by whatever VL was there, because VL is equals to 0. So this was VL, and so it just gets subtracted and just follows the integrator after that. So it's a simple question. And if I give you a parallel RLC, I'll probably, just to make the make the problem simpler, I would give you a voltage source and then give you a parallel RLC, like let's say this. And let's say I told you to find out the current through this. Again, this will be a simple problem again because the voltage across this are all fixed. So if I give you some profile of the voltage now, through the current it is linear, capacitor again it's CdV over dt. The current for inductor is the integral. It's kind of the dual of this circuit, like the parallel RC. Series RLC. Okay, this question was really to give you a feel on, what a pole zero location does to, so I don't want to go much into it. I'll just, so that's why I kind of show pictorially. So in a system, if you have poles in the real axis, that's over here, then your responses are always asymptotic response. In other words, they look like RC time constant. So there's no ringing, there is no fundamental frequency component to it. Now, as the pole starts moving in the j omega axis, then you're going to get these ringings, right? Your voltages. And so basically, depending on which side of the quadrant you are, you'll have both the ringing as well as the asymptotic plot. Like as you can see over here, as we go higher, you get the ringing higher, but at the same time, because you are farther away from the j omega axis, and you can go back and look at the solution. Actually, I'm not sure if I put the solution yet. If you write basically e to the power minus sigma t times e to the power t by tau, so this will one of them will give you the sine component, one of them will give you the decaying component. And the decaying component gets longer and longer as you go in this direction. And the sine wave gets faster and faster as you go in this direction because that's your j omega axis, right? So that's really all I want to say. Okay, I haven't covered this, but I thought I'll mention this because this is something I think a lot of the interviewers might expect you. Charge sharing. So charge sharing is very important because in a lot of IC or electronic circuits, you do switch capacitor or like charge pumps and all that. So it's good to know just the fundamentals of charge pump. For example, let's say you have a capacitor, some C1, and you take a voltage source, let's say some voltage source V1, right? If you apply it across the C1, since there is no, and this is at steady state, so it's charged, so you'll get some positive charges here, negative charge, which is equal to this positive charge, and that Q is equal to C1 times V1, right? So, and that's probably the key. Like in charge sharing, always remember to conserve charge, okay? Now let's take another capacitor, for example, some C2, and there was no charge across it to begin with. Now you take this C1, which was charged to this V1 voltage, disconnect it from the capacitor, and you put it across it, right? And that's a charge sharing problem, classic charge sharing, the simplest charge sharing problem. Now the question obviously would be, what's the voltage across this effective capacitor now? What is this V dash or V1 dash now? Now again, the key to this question always is charge conservation, right? So this charge, which is going to be shared between these two capacitors, the total charge over here, Q, should still remain the same, which is previously, like before, C1 times V1, because like I said, C2 did not have any charge to begin with. Now you want to find out this new because your effective capacitance has changed, which is now some V1 dash times C1 plus C2, right? Because you have two parallel capacitors, the effective capacitor becomes addition of that. So in other words, V1 dash is equal to C1 times V1 over C1 plus C2. And that's a basic charge sharing. So make sure you understand this because, somebody asks you this question, you should at least know this. And you can obviously have variation of this problem. For example, they'll give you that C1 is charged to plus minus V1, and let's say that same capacitor C2 is charged to minus V2, and now you take them and join them together, C1, C2. What's the voltage now? It's the same as this principle now. Q is the addition of C1 V1 minus, because it's a negative charge now, and that should be again equal to C1 plus C2 times the effect, the new voltage, and V1 dash should be equal to C1 V1 minus C2 V2 over the total capacitance, right? And also always remember, let's say I take these two capacitors and make them in series, like that. This charge which was there initially has no way to get replenished, so it will always remain that same charge. And if you had some charge over here, they'll remain as it is, even though if this is connected to ground, because there's no way for this charge to change, no way for this charge to get, so the charge will remain. You need to have some source or some impedance for the charge to get shared. So if I take this capacitor and just put it in series, for example, then it'll just V1 and V2. Let's say the V1 V2 was it's negative. It'll just be V1 minus V2, because there's no way to get a charge shared now, because this charge here has nowhere to go. In order for it to go from this Q2 charge to something else, that charge should have a path to ground or a VDD, some low impedance path. If I just do this, that charge will remain as it is. So remember that as well. Okay. RC time constant, there's really not much. I just want, just make sure that you understand simple RC time. So let's say you had a voltage, you get a step voltage, some V0. And let's say I asked you to find out, VI, let's say step voltage, and I asked you to find out V out. It's simple RC, so you should know how to calculate this, right, with RC time constant. Or it could be a CR as well, and you should be able to write that equation and do it. So just, review your network theory a little bit to just know these questions. Diode circuits, just know the basic functionality of a diode. So for example, if this is a diode and I put a VD across it, and that's the current, obviously everyone knows, kind of simply it looks like that. That's your breakdown voltage. And this is typically about 0.5 volts. And the current kind of exponentially increases. So when you give you a diode circuit, usually there'll be very simple diode circuit. One example will be like, let's say I give you, this is 10 volts with respect to ground, obviously. This is forward bias diode with ground. And if I ask you to find out, obviously if I ask you to find out what the voltage is, you'd probably say this is close to 0.5, because as you can see, any amount of current ID, this is VD, right? So I'm just exaggerating it. Any amount of current here should give you about close to 0.5. If I tell you to find out exactly, I have to give you all the diode parameters. But typically, like if somebody is asking you diode circuits for digital circuits, it is assumed that if there is any current flowing through it, automatically the voltage is 0.5 or 0.7, whatever they've given you, right? So let's say this was 10K, and I ask you, oh, what's the current flowing through this? Then you say D is equal to 10 volt, 10 minus 0.5 over 10K. And so that's what, 0.95 milliamps, right? I think you can ask Dr. Prakash or other faculties for digital circuits. I think some of your gate questions might have digital circuits based on diode. One example is like, for example, let's say I say 10K, this is some 10 volts, and I give you two parallel diodes like this. And this is some voltage V1, this is V2, and that's your output here, V out. And this is like a very old logic, diode-based logic, which people used to do digital gates. Obviously, we don't do that anymore, but people might still ask you to see, your concepts about diodes and all that. And as you can see here, if V1 goes to 10 volts, V2 goes to 10 volts, then these two are off, and so this V0 will just get pulled to 10 volts. If any one of them are grounded, then this voltage will become 0.5 volts, which you probably can think about it. It looks like an OR gate basically, or a 0 gives you 0. Yeah, it looks like an OR gate. So different combinations of this can give you different gates. So just know them in principle, how they function. So that's all I wanted to cover. MOS transistors, simple, like so this is an NMOS transistor. Like as I said, you have an N plus region, two N plus regions, and the main thing to remember here is that it's a symmetric device, right? So the source and drain are not defined till you actually bias it. So a lot of times we'll show it directly, but that is to make sure that you bias it in such a way that it is shown that way. For example, here I've shown, this is your source, this is your drain. I haven't shown the bulk, but assuming the bulk is connected to this is the gate. So in order to have it in the active region, to make it on, your VGS should be greater than 0, usually greater than VTN. VDS should be greater than 0, and then your ID flows from drain to source in an NMOS. Now, if I draw it this way, but actually I connect the voltage sources in the opposite fashion like that. Although I've done it this way, actually, you should have the arrow this way, and this should be your source, this should be your drain. That's what I mean. Okay, so be careful when you see this. So that's what I mean by symmetric device. If I change the polarity, like for example, in a BJT, it's not a symmetric device. An emitter is actually manufactured such that this is collector, this is base. You can't swap the terminals. In a MOS, you can. This is a PMOS device. That's how I'll bias. I just took that example which I had given you. I don't think I want to go through it deeply, but I think I covered pretty deeply in one lecture. If you're given a PMOS, make sure you get your voltages directions right. As you can see over here, VGS is a negative voltage, or VSG is a positive voltage. So your VTP is also a negative voltage. V effective is a negative voltage. So if you want to calculate ID, for example, you want to make sure like you apply the right polarity. And if you feel confident, you can take magnitudes of everything. Just make sure you're consistent with whatever you follow. MOS is a capacitor. Again, just quickly go through it. If you just take the two terminals, short it, and apply a gate voltage that acts like a capacitor, which means that after this threshold voltage of the gate, charge, this charge, which is called inversion, because the channel gets inverted from a P-type to an N-type. So channel charge starts forming just like a capacitor. So your charge will increase linearly with VGS, so the slope of that should look like Cox. By the way, Cox is the capacitor density. So if you have W times L, then the total CGS will be Cox into W times L. And if I draw it as a capacitance, this is how it will look like roughly. If the voltage is 0 to VTN, the capacitor almost looks 0. After VTN, it slowly starts getting to whatever is your oxide density. This is called the accumulation region, but you don't have to worry about it. So this region, you can forget about it. Mostly you will be asked about this region. And if someone does ask you, just make sure you know that. So in the accumulation region, if you make the gate positive, because this is a P-type, you'll start accumulating positive charge, so it'll still look like a capacitor as well. It just won't function as a transistor. NMOS as a resistor, this is the condition when your VDS is pretty close to 0, VGS is greater than the threshold voltage, then your current equation looks like this, and this term over here is your linear term, and you can see that linear term is dependent on the gate source voltage, so you can actually change the resistor based on the voltage, so that's why it's a voltage controlled resistor, but it's only for small VDS, and for a lot of circuits we actually need that, like for example if you're doing RC, tuning or something like that where the voltage difference is pretty small. A lot of times in IC design we use this. So just remember that when VDS is 0, when you're using this equation, it's actually looking like a linear resistor. So this is sort of the complete characteristics of it. You can see that as your VGS is increased, the total current going through it is also increasing. That's the drain to source current. And this axis is the drain to source voltage. So as you increase the drain to source voltage greater than VD sat, so which is like this region here, the transistor goes to what's called the active or the saturation region, where your current equation is given by this equation here. And in this region where VDS is very small, like as you said before, then it's given by this linear equation here. And this middle portion is where you have both the terms here, but most circuits we actually will never operate in this region. So I would say don't worry about knowing the equation in that region. Most of the time, 90% of the time, you'll be actually using this equation. So make sure you know by this by heart. Again, in a test, I would generally not require you to memorize this, but like I said, in interviews, they'll expect you to know some of the basics. So I would definitely memorize this equation and this equation as well. MOS output impedance, just a quick, like this one I showed you as flat, but in reality it's not flat. Now, when you're doing most of a hand calculation, we always use this equation because it gets you to predict the circuit values pretty close. So you don't have to use the entire output impedance equation because it makes it complex. But in reality, there is a certain output impedance. So your current increases as your VDS is increasing, and that's given by this extra term over here. And this lambda is your process constant. So for a typical process, this value will be given to you. Okay, so quick introduction on small signal modeling, which sometimes will be called as incremental method. So if you remember, this is for nonlinear circuits. So if you have a nonlinear device or a circuit, you want to linearize it at a certain point because your voltage or your bias point doesn't change much, so it makes your analysis much simpler and gives you a deeper intuition into the circuit by doing that. So we use small signal a lot when we're doing analog circuit analysis. So here I kind of reiterate the 3 steps we usually use. So if you have a circuit, you operate it at a certain DC bias point. So a certain VDs and IDs will be captured for that bias point. Now usually you'll superimpose some very small signal on it. Like here I say it's a music or whatever it is, and you want to find out the response. It's either an ID or a small VD, which is approximately linear, right? That's the keyword. And always remember this response is different for different bias point. So let's say you did a circuit, you biased it you found out VD over ID, and you said, oh, VD over ID is equal to some, 1 over GM times RD naught or something like that. But this is only valid at whatever bias point you calculated at. If that bias point change, you have to go back and change all this. All right, I think that's all. Just wanted to. So if you take an NMOS, which is really a 4-terminal device, typically we always connect the bulk to source, but and make it look like a 3-terminal device, but obviously it's a 4-terminal device. So you have the drain, source, the gate, and the bulk, which is basically your substrate. And if you do a small signal analysis of this, you'll see that it's got essentially 3 parameters to it. As you can see, between gate to source, it's open because there is no impedance because it's just a capacitance. And this is a low frequency small signal model, by the way. If I had a high frequency model, then I would have the capacitor here. Then you have this transconductor here, which is, we usually call it the GM or the transconductor. And this current is proportional to the gate source voltage here. And this is called the body effect. Usually it's a small factor. And if your bulk and source are shorted, then this term is usually neglected. And that's proportional to the voltage from your source to your bulk. And like in most circuits, we usually neglect this to make it simpler, even if the bulk is not connected to the source. R0 is that output impedance we just talked about. So as you change the drain to source voltage, the drain to source current changes very minutely, and that minute difference is modeled as your output impedance here. So that's really your low frequency small signal model. When what it means by low frequency is that you're neglecting all the capacitors, right? The GM is really the slope, that is the IDS over VGS slope at a certain bias point VGS 0. I've written VGS 0, but it's true for VDS 0 as well. So you basically freeze all the biasing, nothing changes. And that's usually, we have derived it to be this expression here, but this is the expression we mostly use. 2 times the drain current over the effective voltage. And the effective voltage is VGS minus the threshold voltage, which is given by this term. Again, try to remember this term as well. I think a lot of people might expect you to know that. G0, which is 1 over your output impedance, again, is the linearized, the slope linearization over DIDS over DVDS. That is basically saying what is the slope of the rate of change of the drain current with respect to the rate of change of the drain to source voltage at a given bias point, and that's usually given by this term here. And typically, if you substitute ID sat with ID, so let's say you just know the drain current, you can use this expression, and lambda is a given for each process, and you'll know your output impedance. And same GS is DIDS over DVSB, that's the rate of change of drain current with respect to the rate of change from source to bulk for the given bias condition. This one, you don't need to know the expression. Hopefully nobody will ever ask you that. So just to recap how to do a low frequency model. So if you have a circuit like this, so for example, here I've shown you have a VGS bias, and on top of that, you're giving a small signal, which I said, it's a music signal or, whatever signal you're trying to amplify or measure. And then you have a certain, because of this VGS, you'll have a certain drain current, which I call this I bias. So if you're trying to find out the small signal response V out over VI, typically what you'll do is you'll find all the small signal parameters for these biases, VGS, VDD, and IB, so which will be basically this GM, GS, RDS, and so on. So that's first you find out. You short all the DC sources, DC voltage sources. So basically you make all independent DC sources 0, which means voltage sources are open, current sources are short. You do that. And from that, you basically derive the small signal model like shown here. Essentially, you substitute all the small signal model. In this case, it's pretty straightforward. It's a small signal model for this. If you had a current source like a current mirror, you would put that current small signal model as well, like here. So like as is shown here, GM and the RDS for the MOS transistor here, which is modeled here. And this R0 is basically the output impedance of IB. Although it is open, you still have a small signal model for it, which goes in parallel to it. If it is given, if it is just shown to be ideal current source, then you just open it, right? And then the small signal voltage source appear across the gate and the source. So that's how you'll develop a small signal model. And then if you're asked to find out V0 over VI, just solve the network equations for this, which is pretty straightforward. And you find out V0 small signal gain V0 over VI. Again, remember, if any of these changes, VGS changes or VDD change, then you have to go back, calculate all this, and then do the recalculation of V0 over VI. Current mirror, I think all you need to know, probably most people won't ask you any deeper than just basically just know that the ratio between the current sources are the ratio between the sizes. And I think we have talked in deeply about how the current sources function. For example, you're trying to get the I in, which has a VGS equal to that, I out, which has based on your W2 over L2. And if all the process parameters are equal, then they're just equal to W2 over L2 over W1 over L1. Just review the material, just know what your output impedance of your current sources are, which is in this case, for example, it's RDS2. I don't think you have to go deep into all the different kind of current sources, cascade current sources, and all that. I think, I would say just ask Dr. Prakash and the faculty just to know what kind of questions are asked in previous campus interviews. I'll ask Mrinal to see if they really, but it's the basic part. The first part which I covered is probably most important. Actually, this is the problem I had given you. This is the MEMS microphone. I would definitely say solve this problem. It'll give you an idea how to solve RC problems. I'll just give you an indication. It's a pretty straightforward problem, actually. I've asked you to find out V in over V mic. Find out at what, if this needs to be 0.5 at 20 hertz, then what should be the value of this R bias? Actually, I should write R bias here. Okay, so in other words, the impedance of this parasitic capacitor, I've said 0.5. You know what it is going to be at 20 hertz, 1 over C omega, right? You find that parallel with R bias, and this is a resistor divider now, so V in over V mic should be 0.5. So just solve that equation and you'll find out. Solve it because that'll give you a good idea of, how to find impedances and, voltage transfer function. It's a pretty simple problem. I think you should be able to solve it. So I would say solve it. And if you have any, doubts about the question itself, you can always ask me. I think that's all I wanted to cover.